All right, now we're ready for 3D equilibrium and generating the equations, and that's covered in the book in sections 5, 6, and 7. There's a ball and socket type joint, thrust bearings, ball and socket joint, journal bearings, and that's the kind of thing we're going to want to analyze. Here's another good example: a crane supporting a load when we know the mass of the crane. And if you look in table 5.2, here's just a few of them. They do like they did for 2D. I won't put them all here. There's a bunch, but they show you what type of free body diagram to draw given a particular constraint. So there's a ball and socket. Considered any kind of rotation, but you can't move it. Hinge, you can't rotate it but one direction, therefore it has response torques. As a general rule, if a support prevents translation, if you can't push on it, make it move in a direction, then it has a response in that direction. The same thing, if you can't rotate it, then that's because the support is keeping it from rotating, which means as a couple. And so you can kind of, you need to look at these diagrams and figure out how that statement jives with these pictures. Sometimes things are supported and you don't need necessarily the moment force, and you kind of have to, sometimes you almost have to work the problem without any and see what you get and work it, and then see if you can work it with, and usually it's going to be a matter of the number of unknowns. Remember that, as we'll see a review here in a minute, you can have 6 equations. Some of the forces in 3 perpendicular directions are 0. Some moments at a point are 0. That's 3 equations each. That's 6. So you can only have 6 things you don't know. So here's some cases where technically that could support rotations, but the hinge doesn't need to, and therefore he's left them off. The way a single bearing or hinge can prevent rotation, providing a resistive couple moment. However, it's usually preferred to use 2 or more properly aligned bearings or hinges. Properly aligned means they don't have to provide any torque, any moment. And that reduces the number of things that you don't know. Here's another one. We've got a hinge, which could provide 2 moments, but if it's, quote, properly aligned, it won't need to. Now, our equations of equilibrium are F equals ma, and the moments equal, net moment equals I times alpha. Our A is 0, our alpha is 0. So equilibrium conditions are the sum of the forces are 0, the sum of the moments at a point are 0. So that gives us 6 equations. You could have less, but you'll get, that means that the most you can only have 6 unknowns, which is pretty restrictive for analyzing a single object. Now, later we'll learn how to take things apart and get at more equations that way. But for now, for a single free body diagram, the most things that you cannot know on that particular picture are 6. So that limits what we can analyze. And in real situations, when things are allowed to be flexible, there are other equations that we can bring in, and a lot of times our supports are meant to, minimize the deflection or the stretch or the compression. So, learning how to do statics doesn't mean you can analyze all of them, because there are other things that can go on too. So we'll be a little bit restricted, but, lots of problems. And we can have what we call improper constraints. In other words, something can be impossible to be in static equilibrium, like we've got here. We have 6 unknowns, but there's nothing restricting rotation about the AB axis. Therefore, this thing couldn't be in static equilibrium. Here's another case. We've got a roller here and a pin here, so that could roll on down. So, and he talks about that. You want to make sure and read through that in the book. He does a pretty good discussion of that. So, here's some examples of free body diagrams. We've got these two bearings, and again, like he said, we're going to make sure they don't have, if it's properly aligned, we'll assume that. And notice the other thing he says is go ahead and assume everything. You draw it in the positive case for that particular coordinate. And then if you get a negative number out, you'll know it's really in the other direction. But if you get in that habit and work from your pictures, that'll help you keep the sign, because the signs can get confusing. Now, one thing we're going to see as we do the 3D is it's much harder, especially in the beginning, to sort of, write down the equations immediately. So what we'll use our math, our cross product, more frequently. We can always do the cross products, and then often it's good practice to go back and say, well, could I have done this without having to do the cross products by just doing moments about axis? It's how you develop your intuition, so that you can do that. Here's a couple of other examples. Here's this free body diagram. This time we do have to provide couples because of that type restraint. We've got a cable here. So I'm gonna go ahead and pause this one now to keep these videos, or stop it, keep these videos from being too long, and I'll do the rest of the example problems in those slides on a separate video.